Okay, we're still 1 minute early, but if you guys have questions about the project, I am happy to go over them while we're waiting. Yes.
I know that we've been through this like 7 million times approximately, but I cannot get my code to look good in LaTeX.
Oh.
I've tried like using verbatim and like minted and all this stuff, but it just like it still goes off the page like when I push through the text.
Okay. So the question is, can you make the code look good in LaTeX? Okay. So I haven't gotten the minted to work in LIX. I can't help you necessarily with that. But what I found is the reason some of my things are made in LIX and some are made in Word is because there's not an easy way to make it look good in LIX. Okay. But I'm not grading you on whether or not your code looks good. So you can have it in there, and if it runs off the page, that's okay. What I would suggest is copying it into Word and just in Word changing that to a PDF, and then including the PDF in your LaTeX document. That's what I've been doing, actually. So, yeah, and when you're in Chrome, for some reason Firefox doesn't work, and it took me a long time to figure out, like, why is it not working? If you're in Chrome and you highlight something and then you push the little copies, like the two little things, it will keep your code and you can paste it into Word, make it a PDF, and then put it into your LaTeX file. And that's just fine. I won't take off any points. And if your page numbering's wrong in the appendix and things, that's fine. I'm not going to take off some points. Which also brings up another point, since I don't actually grade your paper. If your peer reviewer takes off points for something I said, I won't take points off. Please let me know and I can give you the points back. Yes?
I have a question. So how do we run a regression with only the intercept, no x variables?
So if you wanted to make a model with only the intercept and no x variables, right? It's going to look something like you'll do your proc reg, ... and you'll say model, and you'll put your y variables equals, and then you just put nothing.
Okay.
So if you just don't write any x variables, it will run it with just the intercept. Other thoughts on the homework or project? Yes.
So would you like this? I think I just need help understanding the order that you'd like us to do everything in. Like I know I gotta look at multicollinearity. I gotta look to see if I need to transform any variables. I gotta do model selection. I think there's one or two other things. What do you think is the best order for us to start?
Yeah, I wasn't super specific on that because part of it is that they can be done in different ways, and I want you to kind of play with that a little bit. However, if you do the order that I had in here, you'll probably be fairly good.
That's what I've been following, but I didn't want to check.
Yeah. And so, I mean, part of that is like in step 3, I'm like, okay, briefly look and see if you need any transformations, right? And then you check for multicollinearity. Then you run model selection, and then you check again, and you might have to do another transformation. And if you do another transformation, you probably want to run model selection again, right? So like every time you change something, you kind of go back and start through that loop again. Yes?
I think we talked about this before, but if some of our variables are like, what I'm trying to say, like, I guess for a lot of observations, caffeine was equal to 0.
Yes.
I know that beforehand we had talked about if something is equal to 0, if we have a lot of observations that have that we shouldn't take a log of it because you can't take a log of 0.
Yes.
So I don't know what the question is ongoing, but is that, I guess, is that correct? Like,
It is correct. I mean, if you think about log, this is what your original log function looks like, right? And we can't take the 0. And so even if we have 1 0 in there, we can't take the log. So instead of doing the log, can you think of another function mathematically that looks kind of similar, that levels off? The square root. So you'll want to do the square root of x instead.
So even if there's one observation that has 0, then we would want to change it from log to square root.
Yes. So even with just one observation being a 0, you can't take the log of even 1. And since you don't want to delete that observation, you would use the square root instead. Yes?
Can you do a little demonstration about like renaming the data as you go along? Because I'm finding that I have to rerun my code every single time, like the entire thing. the way I'm renaming things as I'm going. I'm just not getting it.
I have seen that a lot. Whenever you guys ask me to debug, it's usually like something that we renamed. Okay. I don't know if there's something specific I can tell you, though, to fix that. Let's see. So part of it is every time that you want to run something, you probably are going to have to rerun a lot of it beforehand.
Okay.
So like proc import gets in there, right? But then like data cells, I need to make sure that's in there every time. So if I've kind of closed out and come back and then try to do things later, I do have to make sure I run that again. Yeah, as far as naming, I mean, mostly like trying to be specific and consistent. I don't think I have any tips, but I'll look at your code if you want afterwards. Anyone else? It's a lot easier to ask now than on Saturday.
Do you have any tips for getting your code to not delete itself?
Is it deleting itself?
Like I have several assignments that I've done, like homework 1 or my project 1 code, and I went back in yesterday and was looking through all of it, and it just like erased. I don't know. Am I supposed to be like clicking autosave, or is it just supposed to do that automatically?
It will not save. It does. SAS does not autosave.
Okay.
So make sure you're saving law. I've never had it delete anything on me though,
Yeah,
like
I was
that
so
was actually
surprised.
saved.
I didn't need it anymore because it's like
Yeah.
I've had a similar issue where when I'm working with it, the one I'm working in will have a little asterisk in the title, and then SAS will kick me out periodically. And I'll go back and I click my assignment and it's blank. But in wherever you're working, that directory will have one with the asterisk, and that's kind of like an auto save. And then when you save it, it gets rid of the asterisk and saves it to the normal file. That's my experience.
So look at the asterisk.
Yeah. And you're saying asterisk, do you mean the little tilde sign right here? Like those?
No, it's not
No?
asterisk.
It'll be in like the name on like the tab, and it just like says.
I have seen up here. I haven't seen over here, but this seems to be an autosave as well.
Yeah. Okay.
Okay. But as far as like just deleting old assignments, I've never seen it do that. It could just be your computer. You could also get in the habit, and this is helpful for anyone that wants to send code to me to debug. If you right-click on a SAS file over to the right, you can download it. So you can download your file. So if you know that yours are getting deleted every time you sign out, you might want to download what you're working on, okay? And if you want to send something to me to debug, please send me your entire file. That's the only way I can truly debug it. Okay, other questions? Okay, then I think we're on 4.1. Okay, so I went over this example just really fast in class. Let's go through it a little bit slower. So if you remember, we're working on penalized regression. The point of penalized regression is it fixes multicollinearity. The nice thing about ElasticNet is it's one way to fix multicollinearity, so it will deal with all the multicollinearity for you. Okay. It will also work as a model selection technique, so it'll tell you which variables you should put in your model. Now, if you have data without multicollinearity, still use ordinary least squares. But if you have multicollinearity, then you come use ElasticNet instead. So in our blood pressure example, we decided to remove like BSA and pulse previously when we just did this ourselves before ElasticNet. But what if we want to leave them both in? Like, what if I picked the wrong one to take out? Or maybe we want them both in. So we'll use ElasticNet. So I imported my data. And we said there's a lot of different ways you can run ElasticNet. None of them are like better than the others. You can just pick one. What I'm showing you is just different ways to code. And also then I can show you like 3 examples. So we're using proc GLM select. Data equals blood, plots equals all. I just want it to give me all of the plots. Yes? Sorry, thanks. Okay, and seed equals 41. So that seed is because we said we're doing cross-validation, which means we're breaking it up into multiple groups, and each group gets the turn to be a test data set. And so we have to tell it what random seed to use to break up the data, just so we get the same results every time. Model will do y equals all of my x variables. Forward slash, we have selection equals elastic net. Choose equals CV for cross-validation. Stop equals none, and CV method random 5. So we want 5 random groups to do the cross-validating. And stop, if you want to kind of hack it, you can tell it how many variables to let in or how many betas, that counts the intercept, to let in before it stops. So in class, we said that it wants to pick the smallest CV press. Remember our press P statistic we looked at before is just measuring how good of a prediction you get. So we want to pick the smallest. So I'd pick this step and stop with the models or the variables weight, age, BSA, and duration is what ElasticNet tells me using this method. Now we skipped over this. This is called the coefficient progression for blood pressure. What this is it's telling you as each variable comes in, what is the slope coefficient for the different variables. So when I have the intercept, or when I just have the intercept, all of my variables are just equal to 0. When I add in weight, then weight now has a slope coefficient of like 0.5. When I add age, then age has a slope of about like 0.1, and weight went up to about 0.6. So you can see how are the slopes changing based on what variables are in there. Or when I have body surface area added in, you can see body surface area is this like 0.1, age goes up to like 0.25, weight goes up to like 0.7. Usually you'll see the variables kind of level off. Their slopes kind of level off and aren't changing as much. But you can see what happens as each variable comes in. I thought this was really interesting. Do you remember, so weight and pulse are multicollinear. That means they affect each other. So when pulse comes in, it actually had a negative slope right here. What happened to weight? So as pulse came in and kind of took blood pressure down, then they kind of had to make this weight coefficient go up a little bit. That's just showing you how multicollinearity works. Like if you're going to suddenly start using pulse, then your weight has to kind of change a little bit for everything to balance back out. Looking at the CV press, so up here we had the numbers for the CV press. This is in an actual diagram. And you can see at the duration one, that was the 3.6. But I looked at it and said, well, it kind of looks like I was plateauing. Like at 3, when they added body surface area, I was at 3.8. And when they added age, I was at 6.8. That's just looking at this table right here. Okay, so that's where these numbers are coming from. So I might ask myself, is it worth it to go all the way to adding duration, or did I kind of plateau maybe back at this step? So if you wanted, you could maybe stop after body surface area, or you could keep going all the way to duration like ElasticNet says. Either one of those would be acceptable answers. So we'd pick the model, with weight, age, BSA, and maybe duration. It's kind of what I would get from that plot. Now, the best way to decide if you want to include that duration or not is have your training set and your test data set, run them both and see which one gives you better predictions, right? And then that's kind of how you tell. But we're not done. ElasticNet gives us a lot more plots. So let's look at those. So that's the main one. Kind of whatever you ask for is what it's going to give you there. But then it'll also give you the other ones that you didn't even ask for. Okay. So you can see we have AIC, AICC. Do you remember what's the difference between AIC and AICC? One has a C, great, yep. And it stood for corrected. And what was it useful for? Smaller data sets. Okay, basically does the same thing, just smaller data sets. We have the Schwartz-Bayesian criteria, the SBC. We have adjusted R-squared, which is the only one that we want to get big. And we have that CV press, which is the one we asked for and already showed us. Now, what do you notice looking at all of those? So each one will give you a different, like, best criterion. So the star is the best criterion. So AIC says stop at number 6. AICC says stop at number 4. Adjusted R-squared says stop at 6. SBC says stop at 6. CV press says stop at 4. Which one do you guys want to choose? Okay, also, the line is the one selected by CV press because that's the one I asked for. So we'll draw a line at the one you asked for, and then stars for each criteria. So when you look at this, what model do you guys want to choose? And why? Thinking back to what we learned in section like 3.2 when we did model selections. Let's put it this way. Would it be okay if I chose a model with all 6 variables? Yes, I can justify that. I just say, oh, I picked the model selected by SBC, or I picked the model with the best adjusted R-squared. I picked the model selected by AIC. If you wanted to put any of those, no one's going to argue with you. However, do they seem to kind of plateau? Well, I guess before we even talk about how they plateaued, if I wanted to pick a model with just 4 variables, could I argue, oh, I picked the one suggested by CV Press, or I picked the one selected by AICC? No one's going to argue with you. You just say, this is the one I picked. But because they all kind of seem to plateau, could we also pick the one at number 3? They all plateaued, started plateauing around number 3. Okay. So you could pick that one as well. This next one's a different plot. This one plots the average squared error. So average squared error, we've talked about that one quite a few times. It's the same thing as our mean square prediction error, just on the training data set. Remember, it's just the sum of each y minus y hat squared over n. So basically, it's just the average residual. Or sorry, average squared residual. If you just did the average residual, you just get 0 every time. Right, so average squared residual, so the positives and negatives don't cancel out. So this one plots the average squared error, average squared residual. So you can see if we only have the intercept, our residual's pretty high. Right? As we add in weight, our residuals dropped a lot. In fact, if you had to say, like, where did they drop the most, it was when we added weight. When we add age, the residuals drop even more. When I add BSA, the residuals drop a lot. After that, do the residuals change very much? No. The lowest one is at the duration. Or sorry, maybe not the very lowest one. Okay. But they kind of plateau there. So based on the plots, which model would you pick? Okay. We like the simplest one. So I would probably pick the simplest because they all plateau at weight, age, and BSA. But you could add duration still and be fine. But that's what elastic net looks like. It's you run this, you look at all the plots, and you say, okay, which variables do I want to have? Questions on this page? Well, don't worry because we're still not done with our output. Okay. So after it gives you all the plots, it gives you the actual model output for what GLM selected. So this is the model information that ElasticNet picked, or for the model. So the model information for the model ElasticNet picked. So going through, you'll see a lot of it looks fairly similar to ordinary least squares. Okay, we still have our analysis of variance. Like you can still see, oh, wrong one. You can still see like the MSE, the mean square error, where you're still looking for that in our models, right? It has an F value. It didn't actually give us a P value because we're not actually doing ordinary least squares anymore. So like our overall F test isn't going to make as much sense anymore because we're not doing ordinary least squares. You can see things like R squared. That's a pretty high R squared value, right? I'm pretty happy with that one. You have your adjusted R squared, which adjusts for how many variables you put in. The AIC, AICC, all of these were just how to pick the best model. And it gives you the parameter estimates. Okay. So what's your intercept, your age, your weight, etc. So if I was to write the equation of this, we would say something like y hat, sorry, not y hat, we're talking about blood pressure. So my estimated equation, the final product here after I do all of this work, is my intercept, so negative 10.05 plus 0.66 times age plus 0.89 times weight plus 4.29 times BSA plus 0.02 times duration. Because this is the one that Elastic Neck picked based on my cross-validation method that I told it to use. If I don't want duration in my model, I'm going to have to go through and hack my code later, which I will show you how to do. So what if I picked a different choose option? Let's use the SBC, the Schwarz-Bayesian criterion. So most of the things will look the same, so we'll go through them fairly quickly. Okay. But notice, I just say choose equals SBC. I didn't have to say split it into 5 random groups. And notice what else is here? There's no seed because we aren't splitting it into random groups. So we're not splitting into cross-validation groups. So the reason we're running it again is, so basically I can point out you don't need to say seed. SBC, we're still looking for the smallest value, so when you look here, which one gives you the smallest value? It's number 6 with all of the variables, which makes sense. That's what we saw before on the plot. And you can see all of the plots are going to look the same. You can see how do the coefficients change as you add in your variables. Your results will be slightly different because it didn't split everything into groups. So it should be similar, but maybe not exactly the same. You can see that they said the smallest comes at 6 when you add in all the models. And you can see some of my methods are selecting number 6 again, but one of my methods is still selecting number 4. Now, if you looked at these, you could say, oh, 3 of my methods agree on number 6. I could keep all of my variables. If you're like me and you like simpler models, you're like, oh, well, maybe I'll just stop at number 4 because one of them says number 4. And if you wanted to go all the way back to number 3, you could. And you can still see your average squared error. So same thing, this is just saying how good are my predictions. And again, it still looks like we're plateauing around 3. So I would stop at BSA or maybe duration after I've added in one of those. But which model did GLM select if we use the SBC criterion? It would selected all 6 variables. And then I copied just the final output for our slopes and our intercepts. So if you can do it easier on the paper. If you flip back to a couple pages ago where we looked at the model we picked with 4 variables, how did these slopes compare? Let's see. When we had the 4 variables, I think we're like negative 10.05, 0.66, 0.89, 4.29, 0.29, and 0.02. So do my estimates change a bit based on how many variables I have in there? Yes, then you're going to kind of expect that. Again, if you're not really sure which model you should pick, have your test data set, run both models, which one gives you better predictions. Yes?
If, for example, on this one, it says stress is 0.005572. That's very close to zero, so it doesn't make like that huge of an impact doesn't matter whatever you put in that. So could that be an indicator that it's not necessarily, not significant, but like that could potentially be something that you don't include?
So I would look at it, yes, and say, oh, I probably don't need stress because that slope is so close to zero and I could probably keep it out. Now, one little caveat there is you have to remember if they're on a different scale, then your slopes could also be much smaller. So I don't know what they measure stress in, but if they measure stress in like millions, or like if you had really big numbers up in the millions, then yes, your coefficient would have to be really small to compensate for the fact that your values are all like 1 million. Okay. So before you do that, you might want to standardize before you truly pick which variables that way. However, based on everything else and the fact that it seems close to zero, I feel very comfortable leaving it out. So which variable or model do I want to pick? Using everything, I would probably still say weight, age, and BSA. So here comes the hack. If none of my things picked this model, because they all picked 4 or 6, but I feel like this one would be okay because we were plateauing, how can I get it to give me the correct slope values, right? Because we already saw from 6 variables to 4 variables, the slopes change. So if I just take off another variable, I don't know what the new slopes will be. So I have to find a way to get it to give me the right slopes. So our CV method, cross-validation, chose the model with 4 variables. SBC chose the model with all 6 variables. I want to choose it with just 3 variables. Now, the problem is, if this is 3x variables, how many betas will be in there? Because if I wrote it out, it'd be like BP equals beta 0 plus beta 1 times age plus beta 2 times weight plus beta 3 times BSA plus epsilon. Okay. So how many betas are in there? It's 3 variables, but 4 betas. So when I tell it to use the stop option, it always counts the intercept. So I'm going to have to use the stop equals 4 because there are 4 betas if you count the intercept. So I'm going to do the same thing. I rerun procGLM select. I tell it my dataset's split. I want all the plots. I put in all my x variables. Selection equals elastic net. Now tell it a choose method. In this case, it doesn't really matter which choose method you use. I left it as SBC, so I don't have to change my code. You could have AIC, AICC. It doesn't really matter which one because I want it to stop after 4 betas. So stop at 4 betas, including the intercept, which means 3x variables. So once I ran that, I took off all the plots because you don't need to see those again. Now you can see your actual intercept, the slope coefficients, and we can write the equation of our line. So like my estimated blood pressure is equal to my intercept of negative 8.4 plus 0.64 times age plus 0.89 times weight plus 3.96 times BSA. Now the interesting thing here is, if you remember, we had to take out either weight or BSA because they're so multicollinear. We couldn't keep them both in my model when I did ordinary least squares. But here's my final model, and it actually has both of them, which is why we like elastic net. We can leave in more than one related x variable, and it fixes it for us. So we got to include both weight and BSA, even though they are multicollinear. So instead of having to take one out, I can keep them both in. And just for comparison, you can see what were the slope estimates if I just did ordinary least squares with those three. I mean, some of them are kind of close, like weight hardly changed at all, but age changed a bit, BSA changed a bit. It's hard to really tell, like, was all of that extra work worth it? Okay. The way you would tell if it was really worth it is if you actually found the test data set and checked your predictions. But we only had 20 observations, so that's not really enough to split it up. So we're not going to do that here. Questions on that example? Then let's try a different example where it is big enough to split it up. This is infection risk again. We looked at this one before. So we did model selection in section 3.2. We had the variables stay, age, culture, x-ray beds, med school, facilities. Okay. There were 113 observations. Now, I didn't tell you back then, but I actually removed a couple x variables just so that everything would work and we wouldn't have multicollinearity, because I didn't want to complicate that day. So if you looked at some of the other variables that we had, so like I didn't have nurses in there before, and I think I didn't have census and nurses, I think are two new variables. Because if you did a proc reg and looked at the VIF, we got these values. Okay. They were definitely very multicollinear. Even that one is pretty bad. I mean, maybe the 2.9 might be if we went into in-depth, but I can see I at least have some very bad multicollinearity here. And so I took those out. But we don't really like just having to take out the variables. I mean, we do it. Okay. But what if I picked the wrong variable to remove? Like, what if census was actually more useful than beds, which I had kept in? So if I decide to use penalized regression, I can leave everything in, and ElasticNet will just make it all work for me. So this is actually a cool method in the proc survey select, where we're going to make a training/test data set, and then it will use that test data set to actually pick the best model. So pick the best model based on which one gives us the best predictions. So we're going to withhold 20% of the data at the beginning. Hopefully this proc survey select looks familiar. Our data was called infect. I'm going to set a seed, so I get the same thing every time. I'm going to tell it what data set to put all of my selected data in. I want to save 20%. And out all says, give me everything that was already in my original data set. Yes?
Is there any significance to the number you choose in the seed? Is there a reason you don't just go 1, 2, 3, 4, 5 every time?
I type what comes out of my fingers. Yep. So some people say if you have it like 4 or 5 digits long, that it's a little more random. I truly just start typing and stop after 4 or 5 numbers. Occasionally I will do 1, 2, 3, 4, 5 just to see, and that's fine. Whatever I feel like. So then we have, so if you're in proc survey select, basically it goes through and puts a 1 or a 0 by everything. 20% will have 1s, the rest have 0s. So we say data train, set in the infect2, and if selected equals 0. So everything that has a 0 put by it, that's going in our training data set. Everything that has a 1 goes into our test data set. So this is our choose equals validate. So what it will do is it will pick the best models based on minimizing the average square error on the validation test data set. Of course, if we do it on a validation test data set, we learned that instead of calling it average square error, we call it mean square prediction error is what we call it, at least in this class. Now, as far as SAS, they just still call it average square error all the time. So proc DLM select, this part right here is new. Val data is where you tell it the name of your validation test data set. We called our test data set tests, so we just put test there. This part is really nice. Class, med school. So if you ever see something that has an option to put class, that's where you put qualitative variables. It just tells SAS that it is a qualitative variable. Please treat it as a qualitative variable. Now, procreg doesn't have this option. But what it does mean is if I use something like procglm select instead of procreg, and I have things that I need to make dummy variables for, I can just say, oh, this is a qualitative variable, and it will make dummy variables for me, which is really nice. Model y equals all my x variables. Med school still, I still have to write med school here. I still have to tell I want you to check med school. But up here is where I said it is a qualitative variable. Let's see, selections, elastic net, choose equals validate. So I just put in the validate option. And again, stop equals none. I don't want it to stop at any specific point. A few things as you go through, just to kind of like train you to look at these. A lot of times we don't need to look at it, but it does have useful things like dependent variable. That's telling you what was your y variable. Stop criterion, well, we didn't use one. We used elastic net. And the choose criteria, we're doing validation with the average square error. We read or used 90 observation. That's because we split it up. So 90 observations were in our training. And 23 observations were in our test. Our class level information, like you can see, med school was qualitative. It had 2 levels. The values were 1 and 2. I don't really know why that data set was coded with 1s and 2s and not 0s and 1s. But it doesn't hurt anything because if we're doing GLM select and we tell it, here's class, it will make everything work for us. And then this is what we're interested in over here, is it will actually tell you some things. So it has average square error and validation average square error. So this is the ASC for our training. And this is our ASC for our test data. So you can see as it adds in each variable, what was our average square error? How good were our predictions? And you can see how good were the predictions on the test data set. Now we want to, again, pick the smallest value. Because we told it to work with our validation data, it's not going to pick the smallest average square error on my training data. We're going to pick the smallest average square error on our test data. Everything's always more important with how well does it do on new data that it didn't use to train itself. That's more important than the actual training data. So the smallest value we can find would be this one at 0.7824. And that's the one that you can see SAS chose. They said, oh, let's stop after we add in census. Interesting thing here is notice, is that about the same? It's so close with rounding it looks like it's the exact same number. So could we stop at number 5? Probably. This is actually a really interesting thing because what do you notice based on the training versus the test data and the average square error? We actually had smaller errors on our test data. That's kind of rare. It's just coincidence that it happened here. But we usually have bigger errors on our test data because we trained it on our training data. But this is just an interesting one where we get even smaller errors on our test data. You'll notice it still kind of looks the same. You can see what is the slope of each variable as we add more variables. I can see some of them kind of change. Usually most of them will kind of plateau a bit. And this is what I find interesting. Okay, this validation ASC. So it's saying as I add in each variable, how good is the average square error on our test data? So when it says validation, that's your test data. So how good are our predictions on our test data? So at our intercept, the predictions aren't very good. As I add in culture, the predictions get better. Stay is better. Facility is better. X-ray is better. Nurses is better. And then it looks like it's about the same when we add census. And then what actually happens after that? The predictions get worse. That's pretty common. Okay? There's usually some sweet spot where you want to stop. If you keep adding other variables, your predictions will actually get worse. So these ones, our predictions got worse.
Is that due to the penalization?
I don't.
Kind of what we saw in ordinary scores, that like the more you put in, like the slightly better your R squared value would be.
So the R-squared value on my original data would get better and better. Let me see. Okay, there is a picture for that on the next page. Okay, so this page has our training and validation. So it's the average square error versus the variables. This one on the top is my training, and this one is my test. So you are right. On your training data, the more variables you add, we said R-squared always gets better and better. Your predictions will always get a little bit better as you add more variables. And so this one, it gets better and better and better. However, when you move that to a new data set, there's often a point where your predictions get worse. Yeah, so that is a good point. I have to remember to not scroll so fast. It doesn't like it. Okay. I think we finished looking at that plot, though. Now it's really messed up. Okay, so on our test data, predictions got worse if we kept adding variables, which is common. You can also see all the other criterion. So like, what did they say? So AIC said, add them all in. AICC says, stop at beds. Adjusted R-squared, it actually said, add them all in. Okay. And it looked like it plateaued here around beds. So that's kind of where it plateaued. SBC, like it said, stop at beds. And validation ASC said, stop at census. Now, if I was looking at this, and I hadn't specifically been looking at the test data set, but let's just say I looked at SBC or something, and I looked at all the rest of the plots, I might say they were all plateauing around beds, and I might stop at beds. However, anything that is based on the validating on the test data set, that's kind of the one that is the rule over everything else. Okay? So we know that on new data, we actually did the best if we stopped at census. So that's the one I would still go ahead and pick. So even though everything else plateaued around 7, that's all based on just your training data and didn't take into effect test data. So the only one that looked at test data is validation AC, so I'll still stop at that add census. Or even better, since we figured out it was almost exactly the same at nurses, we could stop at nurses. Now, census will be fine, but if you remember back on the previous page, the AAC is like exactly the same if we stop at census or nurses. So we may as well just stop at nurses. So this one, again, is our average square error, but you can see the training data versus the test data. And we said the test data actually got worse as you added in more variables, but it's exactly the same at nurses or census, so we could just stop at nurses. Okay. You can see the output that they gave me. You can see the average square error for training, for the training data set and the validating data set. So this was our train and this is our test data. You can see the mean square error. Remember, mean square error is almost exactly the same as average square error. What's the one difference? Remember? Yeah, the average square error doesn't adjust for how many p's, how many betas. And so mean square error divides by n minus p, which is why its number is slightly different than the average square error. They both measure about the same thing. It's just that mean square error divides by n minus p. You can see all of the slope estimates. Now, it would actually be really ideal if your data was big enough to split into 3 parts. So as we get fancier and fancier, we're like, well, instead of just splitting into tests and training, we actually split into like 3 things. So we use the second data set to help us choose the best model in the training data, which means that we kind of actually use that test data set to help train our model, kind of in a way. So what we really want is now a third part of the data set that we didn't do anything with yet to actually truly validate and make sure our predictions still work on that. We're not really going to do that here in class, but just keep in mind, as you get fancier and fancier, we like to have another third one So anything that you use to pick your model at all is still kind of training, and we still like another piece that we didn't use at all to validate. Now, those model estimates up above were for our 6x variables, but if we wanted the model of 5x variables, we can tell SAS to stop sooner. So if I want to stop with 5x variables, then remember stop includes the intercept, so I'll say stop equals 6. So everything again will look the same. I'll tell it to use my training data. I had to tell it what my test data was. I have this qualitative variable, and I'll say choose equals validate and just stop equals 6. It just says stop at 6 because I don't want the model you picked. I want you to take off that one variable we don't need. And then here's what it is. So basically now census is gone. That's the variable I removed. And I can write down my equation now. I can say my predicted infect values are equal to 1.9 plus 0.1 times stay plus 0.03 times culture plus 0.006 times x-ray plus 0.0005 times nurses. Now this does seem like a really small number, which either tells me nurses might be a really big number, like maybe you have thousands of nurses at a hospital or something, or maybe it is really close to 0. However, at this point, we don't worry too much about that. We just say this is the model that our model selection technique worked. Even if we got small p-values or big p-values, we don't really care. We just say this is the model that we picked based on our validation criteria, or based on AIC, based on SBC, whatever you used. Now, in the end, what do we actually get out of this? Notice we don't have p-values. We didn't do t-tests for our slope. Okay. What do we actually get? We get an equation. And now we can make predictions. Because that's one of the big points of regression, is to be able to make predictions. And we can tell people what x variables are the most useful to make predictions. So once we get out of ordinary least squares, this is actually usually what we want to get out of a model. We're not doing p-values, we're not doing our t-tests for slope, we're not doing confidence intervals and prediction intervals and all those things we learned about before. What we want is we want to be able to give them the equation of the model so they can make predictions, and we want to tell them what were the most useful x variables. And that's what it is. Yes?
Now, remind me, you can't interpret slopes with this process, correct?
I haven't seen anything saying you can't interpret the slope, so you should still be able to interpret the slope here.
Okay.
So we'll add that too. So we could interpret slope the same way. As ordinary least squares. And we hold everything else constant, so we say, so we could do one over here. So we could say, like, if stay goes up 1 unit and everything else stays constant, then the predicted, let's see, infection risk goes up 0.104. So we could do that. Now I said we could interpret the slope. Now the one little special exception here is if two variables are multicollinear, can you hold the other one constant? No, so maybe use your best logic. You probably can't interpret the slope of like nurses and facilities because I think they were multicollinear. So you probably can't interpret those slopes. The other slopes, though, you should still be able to interpret the same way. So we'll interpret slope the same way. Come back. Okay. Except for the multicollinear ones. Multicollinear variables. It just doesn't make sense for them because you can't hold all the rest constant if one's going to be related to it. Yes?
So do we just determine, like let's say we're given a new data set and we run the proc reg and we look at the VIF of it and we're like given those numbers, is that where we're getting these assumptions that these variables are multicollinear?
Yes. Yeah, that is. And I think I showed that on this one, right? What page do I have that on for this data set? So yes, we always start with procreg. Okay. And really, you can still use procreg. I'm not going to tell you that you can't take out one of your x variables to fix multicollinearity. But if you don't want to take out some of your x variables, you want to keep them all in, and then you can use ElasticNet instead. But yes, here I ran procreg. Here's my VIF. I'm like, oh, I have huge multicollinearity. I could take some out, or I can use ElasticNet. Yes?
So is it always going to be an either or? Like, is there ever like one better than the other, taking one out versus keeping them all in?
Sometimes on domain knowledge, it will say like, I think both of these should be in the model, and I want them both in the model. So then you probably definitely want to use ElasticNet. Otherwise, you could take them out, you can keep them in. It's not a huge deal either way. We did say we like ElasticNet because it works if you have a lot of possible x variables and not as many observations. So in that case, yes, you use ElasticNet, but that's kind of a different thing anyways, not necessarily multicollinearity. So you could do either one, and when you get to final projects, you can do either one, and that's fine. Yes?
So this is on a different topic. The quiz, it still says the quiz is this time. Is that right? Or
Yes, I think we can take the quiz tonight, and we should be good on that. Okay, I'll see you next week, or Friday. Come Friday.